Okay, today is almost a review of the 25 years research in oxide semiconductors. Okay, this view graph shows that the highlight of our research. The top one is a glass semiconductor. Glass semiconductor TFT is now widely applied to drive various types of display. For example, your iPad or the large size OLED TV are driven by our amorphous TFT. The second is, this is my favorite word, as a calcium aluminate.
Sir, sorry to interrupt you. Can you put it in slideshow mode? Full screen mode.
Full screen mode?
Yes, no, yes, please.
This is full screen. Oh, please, full screen mode. Full screen mode. Where? Full screen mode. Full screen
yeah,
mode.
At the bottom you can. There is a slideshow menu at the bottom. You can.
Oh. 던졌다. Okay.
Professor, you please continue. I think.
Okay. Can you see?
Yeah, it's perfect now. Yeah.
Let's go ahead because we still see everything.
Okay.
We even see more.
Yeah.
Okay. Yes. Good.
Yeah, so the second is a calcium aluminate. This is typical insulator, but when as a part of the oxygen is replaced by electrons, we can obtain the transparent metals. Okay, so when has a small particle of the ruthenium laureth on its metallic calcium aluminate, this material shows the pretty excellent catalytic activity of the ammonia synthesis at mild condition. We are now focusing on this research. And last one is we first created the transparent P-type semiconductor. So in the course of the improvement of the P-type semiconductor, we discovered ion-based superconductors. Ion-based superconductor has grown to a new continent of the high temperature superconductor comparable to the cuprate superconductors. Okay, this is the outline of my talk today. And first is the progress in the science, especially the origin and the doping of the carriers. Second is the new frontier of the transparent oxide semiconductors. This is a traditional transparent oxide semiconductor. We extended these old territory to these regions. The third one is amorphous oxide semiconductor and the TFT. And the fourth, the P-type and ambipolar oxide. Last is a summary and challenges. Okay, let's move on. The common feature of N-type oxide semiconductors. Oxide semiconductor is mostly N-type. Why N-type? The reason is quite simple. This is a pretty old, 40 years before, John Robertson published a good paper on why tin dioxide shows that high mobility conductors. So that this is a calculation by tight binding method. So that we focus on the bottom of the conduction band. Bottom of the conduction band is dominated by tin 4s orbital. Okay, so that the crystal structure is almost like a rutile, so that the octahedral coordination is connected by sharing the edge, so that distance between the metal distance is so small, so short compared with the edge sharing. So that's why the true design concept of the N-type transparent semiconductor is very simple. Post-transition metal with extended s orbital. and shorter metal-metal separation is much better. That's why edge sharing structure is much favorable than corner sharing. So this is a component, a 5 component of the traditional oxide semiconductor: indium oxide, tin oxide, cadmium oxide, zinc oxide, and gallium oxide. So most of the oxide semiconductor chemical composition fall in this trigonal bipyramidal. Okay, so the second progress of this area is the origin of the electron donor. This is also the tradition, very old work by Fan and good enough. So that they propose that the origin of the electron donor is a shallow donor that's originated from the oxygen vacancy. When the oxygen vacancy concentration goes up, so that the flame level enters the bottom of the conduction band, that's why the degenerate conduction is induced. Okay, anyway, oxygen vacancy was believed to be a major source of the carrier electron. But past 20 years, especially 10 years, this widely believed model was not so common for the most of the oxide semiconductors. Okay, so it's a similar group proposed a model. Okay, that the first is Chris group and Zunger group and Ober's group. So the most of them claim that the oxygen vacancy, energy level of the oxygen vacancy is much deep, so that cannot work as a shallow electron donor. This is almost a common claim of these groups. Oxygen as energy level of oxygen vacancy is much deeper. Around here or the top of the valence band. So what is a plausible electron donor? So that the plausible model is the hydrogen. Okay, this is Gianotti and Van der Waals model. So that his model is very simple. So that zinc and hydrogen form a zinc oxygen bond. So the antibonding electron is antibonding level is occupied by one electron, but the bottom of the conduction band is much deeper than here. So the electron is more dropped to the bottom of the conduction band and work as a carriers. Okay, so my understanding is it's more simple. Okay, oxide is ionic, so the OW minus is substituted with H minus, generates the H minus electron carrier. So this model, so the H minus substituting the oxygen minus, oxygen double minus gives the electron carrier. This model can be applied to the superconductors. So this is our work. So that ion-based superconductor in this superconductivity is induced by electron doping. That is to say, a part of the oxygen is replaced by fluorine, and the generated electron is transferred to the conduction layer, and as antiferromagnetism disappear, instead superconductivity and come out like this. But the problem is how heavy doping was impossible. So we applied this idea, that is to say, OW minus is replaced by H minus. Okay, so the synthesis is a little bit complex, but anyway, result is very simple. So a part of the oxygen is replaced by, this case is deuterium to measure the neutron diffraction. The observed pattern perfectly fit the H minus substituted model. Okay, and carrier concentration is what's evaluated by Hall effect. Electron concentration is continuous going up. So that this is inverse of the Hall coefficient. But anyway, carrier concentration is increased with increasing its doped hydrogen content. Okay, as a consequence, we succeeded in heavy electron doping. the previously maximum carrier concentration was almost 20%. So that yeah, almost like a single TC dome. That in reality, and we found that the two dome structures, as this dome is much wider than the previous one. But anyway, it's H minus doping, and it's substituting O double minus is the new way to dope electron to the oxide. Okay, so the second question is what type of doping is possible to given the oxide? Okay, so that we believe that the band lineup give answers. So we systematically measure the bottom of the conduction band and the top of the valence band, and it's measured from the vacuum level. So the electron affinity and ionization potential for various type of the samples. So each sample was prepared at our lab, so that the data is pretty consistent. N-type semiconductors, the electron affinity is always below this line. On the other hand, the P-type semiconductor, ionization potential is larger than, smaller than this line. So the CBB is a requirement to be a transparent semiconductor, so that not so easy to realize that both of the electron affinity and ionization potential meets this range. So the silicon and the germanium perfectly meets this requirement. So that this is we call the doping window. Okay, so that yeah, I showed that calcium aluminate cases, and yeah, simple calcium oxide impossible to meet this doping window, but the calcium aluminate satisfies this region. Okay, so doping window for electron doping is electron affinity smaller than minus 3.8. So while the whole doping ionization potential should be smaller than 6 eV. This is the doping window. This is almost it's common for the various type of the semiconductor, so including the nitride and it's a phosphide. Okay, from here I show that the frontier extension of the transparent semiconductors. So the zinc, cadmium, indium, gallium, and tin is a classical semiconducting oxide. Of course, the TiO2 is inside of this region. So that the problem is how to beyond this territory. So the aluminum oxide is of course insulator. Germanium oxide is the insulator, but we would like to convert the aluminum oxide-based material to a semiconductor, or the germanium-based oxide into a semiconductor. Here I'll show that one example. So the strontium germanate. This is people. This is well known, and dielectric material, insulators. So strontium germanate has two polymorphs. One is ambient phase, so the octahedral coordination along the germanium. This is insulator. And the other phase is a perovskite. But the important thing is this is a cubic perovskite. So the bond angle germanium, oxygen, germanium is pi. It's 180 degree. So that we focus on the cubic perovskite. Cubic perovskite is very important. Okay, this is the band structure calculated so that we focus on the bottom of the conduction band. Okay, bottom of the conduction band in cubic perovskite is very deep. Very deep. So this is the orbital drawing of the bottom of the conduction band. So that the germanium 4s orbital, oxygen 2p, and the germanium 4s orbital, the bond angle is pi. So that this level corresponding perfectly non-bonding. In a conventional germanium oxide or the oxide, so that the bond angle is not just a pi, so always this level is corresponding to the anti-bonding nature of the metal oxygen bond. So that's why this level is pushed up. However, in the cubic perovskite cases, bond angle is pi, so that this level corresponding to the non-bonding level. That's electron affinity is pretty large. Okay, so this is bond lineup of the various germanium oxide or the strontium germanate. Okay, bond conduction bottom of the conduction band. So the electron affinity of the cubic perovskite is very deep. That's why we expect that we can dope electron following our doping windows. So we fabricated the high pressure phase of the strontium germanate, and this is a part of the how it is doped. So the obtained is the degenerate type strontium germanate. So this is the transparent and semiconductor. So the mobility is a 12, not so bad. But anyway, so band gap is very small, almost 3B compared to the germanium oxide or the ambient phase. The strontium germanate case is band gap is larger than 5 eV. This case is 3 eV, much less. This is due to situation of the bond angle between the germanium and oxygen. So the non-bonding state occupies the conduction band bottom. That's why conduction band bottom is much reduced, so that we can dope electron. Okay, the next subject is amorphous semiconductor. The essence of semiconductor is controllability of film level by impurity or doping or the outer field. So the amorphous material has a large advantage over the crystalline material and in a process, that is to say, easy formation of homogeneous thin film at room temperature, and the continuous control of the chemical composition and the property are possible. So that if the both essence can be met and in some material, so that this would be a perfect amorphous semiconductor for large area electronics such as the display. But the current the situation is not so simple, a large obstacle. So the common characteristics of the traditional amorphous semiconductor, this is the common characteristic. That is to say, thermal level control is almost impossible by impurity doping or by aging. So the reason is quite simple, structural randomness. Structural randomness means that the large defect state or the localized Taylor state density. That's why thermal level control is almost impossible. Okay, and it's a carrier transport is dominated by hopping because each level it's isolated, so that the band conduction doesn't occur. That's why when a crystalline semiconductor it's compared to the amorphous material, so the electron transport is much degraded. The easy formation, but electron transport is much degraded. So the low mobility means that the mean free path of the electron is almost bond separation. And material, as studied so far, is limited to the covalent bonding system, like a tetrahedral system or chalcogenide. Okay, only the exception is amorphous silicon. Amorphous silicon cases, amorphous silicon cases is hydrogen participated the dangling bond. That's why the defect concentration is much reduced. Okay, but Taylor state density doesn't change so much, so that the Fermi level can be shifted from here to here, but beyond. Cannot beyond the mobility gap. That's why amorphous silicon cases only hopping conduction as occurs in a TFT. Okay, so that we focus on the oxide system. Oxide case, oxide material is basically ionic bonding. So that we focus on the N-type semiconductors. So that this is the comparison between the covalent type semiconductor or the ionic oxide semiconductors. So at the bottom of the conduction band in the covalent system, this is the silicon, and anti-bonding of the sp3 and the silicon controls the bottom of the conduction band. So this is the sp3 orbital. So the bond is highly anisotropic. So in the crystalline state, this bonding is almost perfect. The overlap is optimized. That's why mobility is pretty good. But when as the crystal become amorphous, what happens? So the sp3 is hybridized orbital is highly anisotropic. So the overlap between these two orbital is not optimized. So the mobility is easily dropped to similar order of magnitude. The maximum is 1. This is also true. So the gallium arsenide or the gallium nitride. So I think that the people believe that the amorphous semiconductor is very easy to fabricate, but electron transport property is always degraded. So, the material people focused so far was limited to the covalent semiconductor. We focus on the oxide semiconductor. Okay, so this is a transparent oxide semiconductor. So bottom of the conduction. So the oxide ionic nature means that the nature of the conduction band minimum electron pathway is totally different from the top of the valence band electron hole pathway. As the bottom of the conduction band is primarily composed of the vacant s orbital of the metals, as SN4 plus cases or 5s orbital. Okay, so that in the crystalline state, the large overlap between s orbital is possible, irrespective of the oxygen 2p and is there. But contribution of the oxygen 2p is small, so that and spatial spread of the s orbital is so large, so that the large overlap is obtained. That's why, and large mobility is obtained in the crystalline state. Okay, when such a material becomes amorphous, what happens? So the essence of the amorphous is bond angle distribution. Okay, so that these cases and the oxide cases, so that almost like a string composed of the metal balls. So the stretched state corresponding to the crystal, while folded state like this does to the amorphous state, so that the connectivity doesn't change so much. Okay, so my criterion is principal quantum number n equal 5 or larger than 5. Such a situation is really occurs. So that we examine the sample of the such a system of the amorphous semiconductors. Okay, so I'll show this here the one material. This is the indium gallium zinc oxide. People call the IGZO. Okay, so this material is quite interesting. So that you may know that zinc oxide doped with gallium, okay, or aluminum. So that 3 plus gallium substitutes the zinc 2 plus site. Okay, as a consequence, one electron is generated. So that this is material well known as a transparent metal, not semiconductor. Film level is not controllable. Okay, but these cases, the chemical composition is similar but totally different. Okay, and gallium substitutes the interstitial position of the zinc tetrahedral. So that occupies the trigonal bipyramidal position. Zinc oxide to zinc oxide connected by sharing this triangle. Okay, so that I think that if this material a good quality of this material, thin film, is obtained, this material should work as a semiconductor. So for it's a TFT. Okay, so we fabricated the epitaxial thin film of the crystalline IGZO. Okay, this is the obtained sample. So this is a TM photograph as cross section. So the very clear stacking is observed. So the light white pipe line shows the line of the indium. Okay, so a pretty good sample. So as we expected, this material shows that the very low carrier concentration. So that we fabricated the TFT. So that this is the output characteristic, and this is a transfer characteristic. So that the mobility is pretty large. So the 80 at the time, it's a world record, and also the on-off ratio is 6 or 7 order of magnitude. This is enough. And also this mobility is comparable to that of the polycrystalline silicon. So we realized that oxide semiconductor really work as a channel of the TFT. But this material to fabricate the epitaxial thin film, high temperature is needed, so not so practical for display application. So we switch epitaxial thin film to amorphous. Okay, first we check the formation of the amorphous phase and examine the measures whole carrier concentration and the mobilities. So the amorphous is obtained almost the whole range except the pure zinc oxide and the pure indium oxide. And this is the whole mobility, that is to say the mobility of the electron and at the bottom of the conduction band. So the highest mobility is obtained around 30% of the zinc oxide and indium oxide. But it's such a high concentration of the electron, the system and cannot work as a TFT. So when the gallium is increased, so that the mobility is gradually decreased, so that we focus on around here, almost a 1-to-1 or 1-1 system. So that this is pretty good. So the fluctuation of the chemical composition doesn't give a serious property of the electron transfer. So it's very easy to fabricate that. We expect that the stable TFT would be obtained. So, and we fabricate the TFT on by sputtering on the plastic thin film. So this is obtained and the characteristic of the TFT. So the mobility obtained is 15, which is 30 times higher than 30 times higher than that of the amorphous silicon TFT. And this is histogram of the TFT, almost 100 TFT fabricated in 1 square centimeter of the sample. So that distribution is very sharp. This is S value. This is threshold. This is the turn-on voltage. So such a high homogeneity comes from the amorphous nature of the TFT. Okay, so at the time, I often ask the amorphous silicon guy why your TFT shows a very high TFT mobility. So that we check the reason. So that this is the density of state and its energies. So that this is amorphous silicon cases. Bottom of the conduction band is here. Okay, so that the Fermi level is located here. Okay, so that to induce band conduction, we have to overcome the G's such a high concentration of the trapped state. Okay, that's why it's amorphous silicon cases and to shift the Fermi level from here to here was impossible. Always stopped around here. This is a case of the amorphous exode. So the bottom of the conduction band is here. So the Fermi level is located here. So that from here to here, the maximum tensor density is a 10 to the 8th, 3 order less. That's why we can easily upshift the Fermi level from here to the beyond the conduction band minimum. So as a consequence, band conduction occur. So we can obtain the large electron mobility even in amorphous state. Okay, this is the current understanding of the electronic structure. Okay, so that this is the conduction band. This is the valence band top. Fermi level is located here. Fortunately, it's around the Fermi level, no big dose around here. That's why we could upshift the Fermi level from here to here. But we detected the pretty huge dose above the valence band top. So such a large dose was detected by hard X-ray as photoelectron spectroscopy using a Japanese synchrotron. So that it's a hard X-ray. It's bulk sensitive. So the not so surface sensitive. That's why the sample preparation is not so difficult. And the sputtering is also needed. That's why we can obtain the reliable data. So that, very huge dose around 5 times 10 to the 20. So that when gate voltage is minus gate voltage is upright, Fermi is going down, going down, going down, and stopped around here. This means that it's channel inversion doesn't occur. P channel doesn't work. Okay. This means that in a display application, 90% of the device remain off state. Off state means that it's this state, off state, P channel doesn't open. So this is contribute to the energy saving. Okay.
Professor,
so
sorry to interrupt you. You have 3 more minutes.
Okay, so that you can see that the use cases and the high mobility in the on state and the low power consumption for the end state. So that off state. So that this is a unique feature of that as a transparent oxide semiconductor. Fermi level is controllable beyond the CBM, and it's Okay, this is the current state. This view graph summarizes the progress of the exo TFT as a fundamental research start from 1995. The first presentation was done in Amorphous Semiconductor Conference at the Kobe. At the time, more than 800 papers were presented. The oxide semiconductor is only one. And we fabricate the crystalline exo TFT 203 and amorphous 204. And after that, so that the company fabricated the large size spotting target. This is a photo of the Gen 8.5. Now Gen 11 produced already. So the practical application started for the display. The first is a smartphone, and it's a tablet PC, and it's a PC monitor, and eventually it's OLED, large size OLED are driven by Oxide TFT. So this one is a memorial picture for me. In the 12/17, the president of the LG display has visited our lab to donate 16.5 inches OLED TV. So that now you can buy it's OLED TV and it's at the electrical shop, and it's you can enjoy the very beautiful picture of the OLED TV. So almost the time. Okay, so now this is the last one. So that so that around the 2000, so that gallium oxide was impossible to conduct an electron. So that our group fabricated the transparent conductive oxide of the gallium beta gallium. The band gap is 5 eV. This material is now focused as a power transistor. Okay, so that the polycrystalline and the TFT was reported in 2014. Okay, mobility is the 2, and the on ratio is the 4 order. So that so the 2017 we fabricated the amorphous and gallium oxide TFT. So that so that not so easy to realize the TFT of the gallium oxide because of the oxygen defect concentration so far that eventually we deleted the oxygen vacancy as a consequence. We obtained the almost comparable performance of the TFT as performance to the polycrystalline and gallium oxide. So anyway, it's to make elimination of the trap state in the band gap is a key of the amorphous oxide as TFT. Thank you very much.
Thank you. Thank you very much. Thank you very much. Questions for Hosono Sensei? I just want to mention that your talk is a great illustration for this introductory speech of Professor Sharma, Ashutosh Sharma, because he actually pointed out that in the area of New India, scientists should be more concentrated how to move quickly from fundamental science to application. And your talk is just absolutely excellent illustration. I believe many of the Indians group, and not only Indians group, would dream to have such rapid developments from fundamental, very fundamental ideas of transparent semiconductor to all this huge and impressive fabrication demonstration which you mentioned. I don't see any talks in chat of just one talk. Can gallium-203 will replace FTO in the future of optoelectronics? Yeah. I don't know how to pronounce that element, but I think you can get it. Gallium oxide, but which one? I don't know how it pronounced it.
Yeah, no, gallium, beta gallium. Beta gallium is now...
Gallium oxide?
Yeah. Gallium oxide is now attracting much attention for the power electronics, but yes, the mobility is good, but the fatal drawback is P-type is almost impossible.
Okay. You got another question. What are the main challenges in making large area TFTs?
Yeah. So that now the backplane of the large size display is shifted to amorphous silicon to oxide. Okay, so the IGZO is almost a standard, but the next challenge is more high mobility as oxide TFT. Mobility of the IGZO is a stable TFT is maybe the 15. So the company need more than 30 to fabricate the driver, gate driver. Now gate driver as polysilicon is used as a gate driver. So if the high mobility larger than 30 or 50 is obtained, so the all oxide semiconductor drive a pixel and its surrounding the transistors.
Okay. I have more questions, but we are half an hour behind the scheduler, so organizers will be very unhappy. So I just wanted to mention, Professor Hosono, that you hit the record, 699 participants. So I was expecting 700, but it didn't happen. So so far you're a leader in the number of Indian participants in one talk. Anyway, it's a great talk. Thank you very much. We should go to the next speaker. Thank you.
Thank you. Thank you. So on behalf of ICON 2021, I would like to thank Professor Yuri for chairing this session. Thank you so much.
Thank you. Thank you.
Hi, Yuri. How are you?
Not a bad, but I'm not your chair. You should find your chair. My job is over.
Well, if you can't find my chair, and then we'll make you to be the chair, you know. So thank you.
Hello, Professor Jagadish.
Yes.
Yes. This is Kiran.
Hi, Kiran. How are you?
I'm fine. Thank you. Sorry, we are on late actually. Some 15
no,
minutes.
That's okay.
Or so.
That's okay.
So,
yeah. That's all part of life.
Yeah. So thank you. So now I welcome to the keynote session, day 1 keynote session 2. Now the keynote lecture 3 by Professor Chinnapati Jagadish. Before we invite Professor Jagadish, I would like to invite the chairperson for this session, Professor Shanti Prince. She is the head of the Department of Electronics and Communication Engineering at the SRM Institute of Science and Technology. Professor Shanti received the Optical Society of American Foundation funds towards COVID-19 for building UVC decontamination chamber for N95 masks. And she also received IETE COET 94 award 2016 for the contributions in the field of biophotonics for the year 2016. Dr. APJ Abdul Kalam Inspiring Teacher Award instituted by IET CLN for the year 2014-15. And she received Career Award for Young Teachers All India from the All India Council for Technical Education, New Delhi. And her research interests include free space optics, underwater optical wireless communication, space applications, visible light communication, optical wireless channel modeling, passive optical networks, fiber wireless access networks, all optical signal processing, optical cryptography, photonics in 5G, integrated photonic devices, etc. With this small introduction, I invite Professor Shanti Prince to take over the session, to chair the session. Thank you.
Yeah, a very good afternoon to all of you present over here. I could see a huge gathering here waiting to listen to Professor Chinnapati Jagadish. I am greatly privileged and honored to introduce such a great personality. And in front of these persons, our contributions are very meager. And I just want to introduce Professor Chinnapati Jagadish to the audience. Currently, he's been received the highest civilian honor awarded by the Government of Australia, Companion of Order of Australia. We congratulate you, sir. And he was educated in India and worked in India and Canada prior to moving to Australian National University in 1990, where he has established a major research program in compound semiconductor optoelectronics and nanotechnology. He is a distinguished professor and head of Semiconductor, Optoelectronics and Nanotechnology Group in the Research School of Physics and Engineering, Australian National University. He is also serving as Director of Australian National Fabrication Facility, ACT Node, and convener of Australian Nanotechnology Network. Dr. Jagadish has published more than 820 research papers and holds 820 research papers, holds 5 US patents, co-authored a book, co-edited 8 books and edited 12 conference proceedings and 15 special issues of journals. He is serving as Vice President and Secretary Physical Science of the Australian Academy of Science. Professor Jagadish is serving as an Editor-in-Chief of Progress in Quantum Electronics, an editor or associate editor of 6 journals, 3 book series, and serves on editorial boards of 19 other journals. He holds honorary positions at University of Electronic Science and Technology of China, University of Tokyo, Anna University, Mangalore University, ICT Mumbai, Oxford University, and the list goes on. He won the 2000 IEEE Millennium Medal and received Distinguished Lecturer Award from IEEE NTC, IEEE LEOS, IEEE EDS. He is a fellow of Australian Academy of Science, Australian Academy of Technological Sciences and Engineering, IEEE, APS, MRS, OSA, AVS, ECS, SPI, AAAS, IOP, IET, ION, and Australian Institute of Physics, AIP. He received the Peter Baum Award from the ANU in 2006, the Quantum Device Award from ISCS in 2010, IEEE Photonic Society Distinguished Award in 2010, IEEE Nanotechnology Council Distinguished Service Award in 2011, an Electronics and Photonic Division Award of the Electrochemical Society in 2013, Walter Boas Medal 2015 IEEE Pioneer Award in Nanotechnology, and the list continues. And he received OSA's Nix Holoniak Junior Award as well. He has served as a president of Australian's Material Research Society from the year 2016 to 19 and president of IEEE Photonics Society in the year 2018 and 2019. His research interests include compound semiconductor optoelectronics, nanotechnology, photovoltaics, and neuroscience and neurotechnology. I welcome Professor Chennupati Jagadish to address the gathering and deliver his keynote address.
Thank you very much, Professor Shanti Prince, for that kind introduction. And so I'm humbled and grateful for this honor to speak to all of you at this ICON 2021. I want to really especially thank all the organizers, particularly Professor Karthikeyan and then Professor Kiran Mangalampalli and all the organizers for inviting me to participate in this conference. So as been mentioned that though I work at the ANU, I have honored appointments in various parts of the world. And it's a really pleasure and honor for me to work with my colleagues in various parts of the world. Before I proceed further, I would like to acknowledge my collaborators. And this is the work which I'm talking about today is a collaborative effort between my group at the Australian National University, many groups in Australia, US, UK, China, Korea, Sweden, Italy, Russia, Switzerland. So the beauty of science is that there are no national boundaries. We can all work together. And so that's what really the fun part for me. And then I've only listed the professors' names here. Many students and postdocs in these groups also contributed to our work. And I want to thank all of them for their contributions to our joint research. And without their hard work and commitment, there's nothing much to talk about. This is my group at the Australian National University. And then typically about 10 to 12 nationalities at any one time, bright young people. And again, it's a real pleasure to work with these bright young people. And then again, these are the guys, those who really make things happening in the lab. And I want to thank them for all their contributions to our research. And also want to take this opportunity to thank our funding agencies for their support, allowing us to be able to carry out the research. Here is the motivation overview of my talk, and I'll give you the motivation why we're interested in nanowires, and I'll talk about how do we grow these nanowires and nanostructures, and I'll talk about nanowire lasers and LEDs and terahertz detectors and nanowire solar cells, and I'll finish off with the nanowires for neuron growth, and I'll draw some conclusions. So before I proceed further, I would like to acknowledge many groups, those are working in the field of semiconductor nanowires in various parts of the world. And then we learn from each other and then build the knowledge from each other's contributions. And I want to thank various people globally working in the field of nanowires. And so without their contributions, our field will be poorer. And then we are always learning from others' contributions in the field, and I want to thank them. So before I proceed further, in terms of fourth industrial revolution, and we all know about the first industrial revolution, steam power led to mechanization, and second industrial revolution, electrical power led to mass production, and then third industrial revolution, computer power led to automation. And fourth industrial revolution, people are predicting that the digital world and then the biological world will come together. And then most of this communication could be through light and the sensing and interaction of light between humans and machines. So because of the fact that we receive 90% of our information via light. So light-based technologies currently are about $1 trillion, and that people are predicting by 2030 or so, they'll be doubled or so. So that means there's a lot of potential for us to be able to develop various technologies. So as part of our Center of Excellence, TMOS, and Transformative Meta-Optical Systems, we're developing various technologies and in terms for the next generation optical systems. So the World Economic Forum has identified the future technologies needed for the wide variety of applications, including holographic displays, wearable optical sensors, light navigation and communication, autonomous vehicles, and 3D vision and gesture recognition, enhanced machine vision, and augmented reality. They all will be requiring fundamentally new approaches for smart and miniaturized optical systems. So that's why we're interested in developing nanoscale optical systems and microscale optical systems. And that's what our aim of our Center of Excellence is. So optoelectronics, what is optoelectronics? And we've all studied about electronics, and then we know that nowadays, we're all using computers or any smart device, and then of course there is electronics is there, and they're all made out of silicon, and silicon is the workhorse for the microelectronics and nanoelectronics industry. But unfortunately, silicon is not a very good light emitter because of its indirect band gap nature. So that's where you need to have a direct band gap semiconductors in order to be able to emit light. And that's where compound semiconductors of group 3 of the periodic table and group 5 of the periodic table come into picture. And in this case, we work on gallium arsenide, indium phosphide, gallium nitride, aluminum nitride, indium nitride, gallium antimonide, combination of these materials. Different materials have got different band gaps, so they emit the light of different colors or detect the different colors of light. And that's why we're interested in really making use of these ones. So in terms of the developments, and you can see that the development of the blue LEDs, in fact, was a missing link in using gallium nitride technology has led to Nobel Prize for these Japanese scientists in 2014 or so. And then once if you got the blue LED, and then of course with the green and red LEDs available, and then you're able to create white LEDs and then LED lights and other things which are consuming much less power because of the high efficiency of these particular LEDs. And again, wide variety of lasers are made out of these materials. And nowadays, solid state lighting, large area displays are all made out of this nitride technology or so. But also the same materials which are used for making lasers and LEDs, they can also be used for imaging and detector applications. For example, these materials are used for detection of the biomedical imaging applications, or even in manufacturing to identify in computer chips while you're operating them, where the heat is generated, so that heat generation is a major issue in computer chips. How do we really be able to redesign these circuits to really minimize the heat, hotspots and other things? And so again, infrared imaging, really these materials play an important role. And in fact, three-phase semiconductors are really already demonstrated multi-junction solar cells exceeding 47% or so. Today, I'm able to talk to you because of the optical fiber communications, and where the electrical signals from my computer are converted into light signals by using lasers, and then they pass through the optical fibers, and on the other end, we're able to convert these ones into the electrical signals by using photodetectors. Again, indium gallium arsenide phosphide materials are used for this purpose because optical fibers are most efficient in terms of the absorption and the dispersion losses in the infrared region of the spectrum, about 1.3, 1.55 micron window region. So now let me come to nanowires, and nanowires are really, nanowires have dimensions of about 10 to 100 nanometers or 200 nanometers in diameter, and the lengthwise they're about up to for a few microns long or so. So nanowires are seen as building blocks for the next generation electronics and photonics. And one of the unique things with the nanowires is the lattice mismatches are no longer an issue. Once you can have, if you've got a material which got a large lattice constant with respect to the substrate, they can expand without creating dislocations. And you got a material which got a small lattice constant with respect to the substrate, again, they can contract without creating dislocations. You can also create axial heterostructures. In this case, the green material is different than the red material. You can create axial quantum wells and single electron transistors and a range of devices. You can also dope these nanowires, both p-type and n-type, so that means you can be able to make p-n junctions. So because you need p-n junctions for making LEDs or lasers or photodetectors or solar cells, so that means you'll be able to make a single nanowire based these sorts of optoelectronic devices, for example. We can also create radial heterostructures or core shell nanowires, and this red material is different than this pink material, so that means you'll be able to create multi-layers of these structures of the core shell, wide variety of structures, and we and others have worked on these ones. But also we can create the branch nanowires, and you can allows you to be able to create the three-dimensional architectures. So in fact, let me give you some examples from our own laboratory where we have shown we can grow gallium antimonide nanowires on top of gallium arsenide. Despite large lattice mismatch, you're able to show we can make atomically perfect nanowires of gallium antimonide on top of gallium arsenide. You can also create indium arsenide branch nanowires, and we can create the nano trees of indium phosphide. And also we are moving from nano wires to nano membranes most recently, because this opens up a lot of opportunities. And most importantly, international technology roadmap for semiconductors, and these are the guys, those are setting what technologies are needed for electronics. They've identified nanowires as also key technology component for next generation electronics. And so that's why IBM, Zurich and others have got major research programs of integration of 3-5 semiconductors and silicon if the lattice mismatch is no longer an issue. And then in fact, they've demonstrated already indium gallium nitride, gallium arsenide based vertical transistors on 6-inch silicon wafers or so. It's really an exciting development in terms of using nanowires for a wide variety of applications. If the nanowires are so much of importance, and how do we make these ones? There are two main techniques which we use. One is called as a metal catalyzed VLS growth process and vapor liquid solid growth mechanism, which I will come back to. And another technique is called selective epitaxy. And we use a technique called metal organic chemical vapor deposition, MOCVD. And there's also an alternative technique called molecular beam epitaxy. And then you can use either of the techniques and be able to make nanowires. In this case, what we do is that we take some gold nanoparticles. You can buy these things in a colloidal solution these days from 10 nanometers up to 300 nanometers or so. We put a colloidal solution of this gold of 50 nanometers in this particular instance, for example, and then we try to heat these ones and in an MOCVD reactor on a gallium arsenide substrate, for example. Gold, though it's got a melting temperature more than 1000 degrees Celsius, once it starts reacting with the gallium or aluminum or indium, the melting temperature of this alloy comes down to as small as 350 degrees Celsius. So once if you introduce the gases needed for the growth of gallium arsenide, for example, trimethyl gallium and arsine, and these gets incorporated into this liquid alloy of gold gallium, it gets supersaturated, crystal starts precipitating out, and gold is always sitting on the top. So really, this is really like, it's like a supersaturation is taking place. Like if you keep on putting more and more sugar into water, you can dissolve sugar in the water up to some time. And once if you exceed the solubility limit, sugar crystal starts precipitating out, and the same thing happens here. This is the work of my former student, Dr. Hannah Joyce, who's now an associate professor at Cambridge University, where she has demonstrated by developing a technique called two-temperature growth process, where she was able to show that we can really get excellent nanowires of cylindrical shape. And then in this case, I'm showing you nanowires of about 50 nanometers in diameter, because she has used 50 nanometer gold nanoparticles in this particular case. You can go to the transmission electron microscope image of these particular nanowires. You can see the gold nanoparticles sitting there. And then you can also see that there are no defects whatsoever, atomically perfect nanowires we were able to make using this particular technique. And then now the rest of the world is making use of this particular technique in order to be able to make high quality, atomically perfect gallium arsenide nanowires. The second technique which we use, selective epitaxy. In this case, we don't use any metal nanoparticles. We deposit some silicon dioxide by PECVD process, and then put some photoresist and do electron beam lithography, and then try to create holes. And we transfer those holes through silicon dioxide so that you can expose indium phosphide in this particular case. And then we put into the MOCVD reactor, heat it to somewhere between 650 to 750 degrees Celsius. And those are the temperatures. Typically, we grow the epitaxy layers, for example, introduce the gases needed for the growth of indium phosphide nanowires, for example, trimethyl, indium, and phosphine. And then the nanowires start growing wherever these holes are there. You can see the ordered patterns of these particular nanowires, and because of the fact that you created ordered patterns of these holes here. You can see the SCM image of this indium phosphide nanowires, and you can see the top view showing the beautiful ordered patterns with beautiful hexagonal facets being nicely seen. And so really, this is the work of Dr. Qian Gao, who is now a research engineer in Blue Glass in Sydney. And then she was able to show that you can get excellent indium phosphide nanowires. And then, of course, we've gone off and looked at the light emission from these indium phosphide nanowires. And then we excite these nanowires with a laser pulse and look at the light coming out of these ones. We've quantified the quantum efficiency as a function of the excitation power. You can see you can get quantum efficiencies as high as 50% or so. And we compared these nanowire performance with respect to indium phosphide epitaxial layers. And then they're also very much comparable, indicating that the surfaces really play a very benign role in the case of indium phosphide. You do not need to do any passivation or anything of that sort. And then really you can get excellent optical quality indium phosphide nanowires by using this selective epitaxy. In this case, because we got these nanoparticles randomly distributed, these nanowires are randomly distributed, we can also create these ordered patterns of these gold nanoparticles. We can also create ordered patterns of nanowires using this technique as well. It's a matter of choice which techniques you prefer to use. And then we demonstrated nanowires based on this technique of the VLS growth process from up to 10 nanometers up to 300 nanometers. In the case of selective epitaxy, we demonstrated nanowires as small as 70 nanometers up to 700 nanometers or so. and depending on the applications, and you really choose the diameter of the nanowires. In this particular instance, I'm showing you the nanowires diameter of about 200 nanometers or so. So we asked ourselves, if instead of opening a hole, what would happen if you open a slot or open a ring in the case of selective epitaxy, for example. This is the work of my student, Dr. Nain Wong, and then where he spent about 4 years in order to be able to really look at this problem and then try to really look at how to get the high quality, wide variety of different structures. Again, we deposit some silicon dioxide and put some photoresist and create electron beam lithography patterns of either holes or slots or rings, and then put this one into the MOCVD reactor. And then he really optimized a wide variety of growth parameters in order to be able to get a good quality structures. And again, I want to really thank my students and postdocs for really producing beautiful results. And they might have spent a year or sometimes 2 to 3 years in order to be able to get the beautiful results which I'm sharing with you. Here's a case where Nain Wong, when he opened this slot along a particular crystallographic orientation of 101 bar, and then he puts this one into the MOCVD reactor and then introduces gases needed for the growth of indium phosphide at temperatures around 700 degrees Celsius or so, you can see you can create a beautiful nanomembranes with this particular kind of facets here. If you open the slot along another crystallographic orientation, and then you can also create these membranes, but they end up having a different facets here. But if you open the slot in between these two crystallographic orientations, you can really create these beautiful diamond-like structures with these alternating facets or so. Now you can see that instead of just making nanowires, it is opening up of making wide variety of structures, and then really for a wide variety of applications or so. Again, when we open this ring structure, again, you can see that you can really create these alternating patterns of these different facets and a ring-like structure. And if you keep on growing these ones, and ultimately the gap in this gets filled up, and then it forms into a membrane. And then if you keep on growing further, you end up finishing off with these low energy facets. And because because ultimately crystals like to be in the low energy state rather than the high energy state or so. And again, there's a lot of amount of work Nain has spent in order to be able to get these nice results. Let's go and now look at the light emission from these structures. And again, what we have done in this case is that we have excited these nanowires in cathode luminescence in scanning electron microscope. And then we excite these nanowires with the electron beams. And then you essentially create electron hole pairs and look at the light coming out of these ones. You can see the top view of the SCM pictures of these nanomembranes and nanodiamonds and nanorings. And you can see the beautiful cathode luminescence images of these structures. You can see the very uniform light emission, indicating that there are no defects, and then optimum conditions Nain has found is really producing excellent light emission from these structures. And in fact, most recently, we've really demonstrated some ring resonator lasers of one of my new students, Wei Wong, is really exploring these particular ones. Mainly, these are useful for integrated optoelectronics applications also. So till now, I've only spoken about the nanomaterials, or nanowires, or nanorings, or nanostructures growth. Now let me move towards devices. All of us have studied about lasers. We said you need to have a gain medium. You need to have a laser cavity by creating mirrors here. You need to pump the gain medium in order to be able to create population inversion. As and when the model gain is larger than the optical losses, the lasing starts taking place or so. In fact, this is a threshold gain condition for lasing. And essentially what it says is that your absorption losses and mirror losses need to be compensated by the gain. Then only the lasing starts taking place. This is an undergraduate optics courses we've all studied. So now it turns out that if you take these nanowires, and then if you shine light from the top, and then if you choose the right kind of nanowires, they act like waveguides, and light propagates through these nanowires, and light comes out to both ends of the nanowire. Because also that these nanowires have got a refractive index of 3.4, and then air is a refractive index of 1. Because of the refractive index, both ends of the nanowires also act like mirrors. So that means I really don't need to create any separate mirrors or any cavity or anything. In principle, these nanowires, each nanowire should act like a laser cavity, and in each nanowire, I can be able to make them as a laser, for example, if everything gets right. We have really been working in this area for a long time, and in fact, we demonstrated a wide variety of lasers. I will not have time to go into all the details. And Dr. Drew Saxena, who is at Imperial College as a research associate and is demonstrated gallium arsenide nanowire lasers. And then Dr. Qian Gao has demonstrated outside indium phosphide nanowire lasers. And then Dr. Drew Saxena also has demonstrated multi-quantum well lasers. And then Dr. Tim Burgess, who is at IP Australia now, is demonstrated zinc-doped gallium arsenide nanowire lasers or so. So Drew Saxena, again, has spent a lot of time in doing simulations and designing these wide variety of lasers. and identifying which optical modes are propagating to these nanowires, and then looking at what's the threshold gain for lasing for these ones, and as a function of the diameter, a fixed length of the nanowires or so. Again, as part of his PhD, Drew has spent about 4 years in order to be able to design and fabricate and then demonstrate these lasers, for example. To really cut the long story short, and then based on Drew's simulations and Dr. Nain Jiang and then Jenny Jiang, she's now a postdoctoral fellow at University of Cambridge. She's really grown these gallium arsenide, aluminum gallium arsenide nanowires, and about 5 to 6 microns long. She transfers them onto a glass slide, and then Drew really does these measurements, and he excites this with the laser pulse and look at the light coming out of these ones. Below threshold, you see a very broad light emission. Above threshold, a very sharp light emission, which is acting like a laser diode here, laser here. You can also see the beautiful interference fringes because of the coherent dipoles that emitted both ends of the nanowire, and he has done the simulations of these particular nanowire, and then the inference fringes are really matching very well. And he also plotted output versus input, and you can see threshold-like behavior where the lasing is taking place. And also he plots a log-log plot where S-type curve, which shows that here you get the spontaneous emission, and here you get the amplified spontaneous emission, and here you end up getting the lasing behavior or so. And this is the first gallium arsenide room temperature lasers. We demonstrated this one about 7+ years back or so. So what are we going to make use of these lasers? And we are making, and this is a collaborative work with Professor Martin Dawson and Professor Michael Stein and Professor Antonio Hurtado at the University of Strathclyde. They developed a technique called the transfer printing technique. In this case, what they come up with is a PDMS stamp. They can be able to pick up these nanowire lasers and drop them wherever you want. And this is a research fellow, Dr. Joel Haber, has spent a lot of time in developing this particular technique. And in this case, they were able to transfer these ones onto PDMS surfaces. And you can see IOP, their institute name they've written, and you can see Institute of Photonics, and then you can see these lasers here. And then they pump these lasers, and they're able to show that all these nanowire lasers are working, and then there's no damage been created during this transfer printing process or so. But then you may ask that question that you are transferring onto polymer surfaces, which are soft surfaces. What about transferring onto hard surfaces? That is precisely the question which I asked them. And then they transfer these one to glass substrates, which are the flexible glass, which we want to make use of them for flexible optoelectronics applications. And you can see the optical image of these nanowires here. And then afterwards, by pumping, they're able to show that they're all lasing. You can see the light coming from both ends. And again, threshold-like behavior and a sharp light emission, showing that all these nanowire lasers are lasing even after transferring onto hard surfaces. So then we asked them that, will you be able to really transfer these nanowire lasers onto nano antennas? This is a work of Professor Fang Ren, who is now returned back to Nanjing University. She has been making these terahertz metamaterials, and she's creating these nano antennas with aluminum or so. There's a gap in the middle, and we requested them whether they'll be able to make these, locate these nanowire lasers in the middle of these nano antennas here. You can see the close-up of this particular one here, a nanowire here, and these are the antennas which are here. So if you don't have any nano antenna, light is coming from the both ends of the nanowire because nanowire acts like a Fabry-Perot cavity. But once we put the nano antenna here, suddenly light starts coming from the vertical direction. So now we're able to really, because of this nano antenna is engineering the radiation patterns, for the first time we're able to demonstrate vertically emitting nanowire lasers. And you can see again threshold-like behavior and sharp light emission. So now that means we're able to really create two-dimensional ordered patterns of these nanowire lasers for meta-optics applications and display applications and a range of things. So really this is looking extremely promising, and that's what we're exploring at this stage. But till now, all the lasers which I showed you are all optically pumped lasers. But ultimately industry wants to make use of electrically pumped lasers. So in fact, this is the work of my student, Dr. In-Suk Yang. Now he's returned back to Samsung as a research engineer. And then he has looked at this one. And then if you want to make an electrically injected laser, you need to have a PN junction. So he tried to dope this indium phosphide P-type, and then has grown a quantum well of indium gallium arsenide, that the yellow layer, and then he put an N-type indium phosphide on top of that one. So then he's put the electron beam lithography, he's transferred them onto a glass slide, does electron beam lithography, and make contacts, gold titanium contacts on both ends of the nanowire, and he starts pumping current and looking at the IV characteristics here. You can see current voltage characteristics show that this looking like a diode-like behavior, indicating that he's able to really make this PN junction, and then be able to really get ohmic contacts and be able to make a PN junction or the diode-like behavior here. If you start injecting the current into these diodes and the laser diodes, you start seeing the increase in the light emission from these ones. And then you can see also you end up getting 2 emission peaks. And this is because of the fact that a quantum well which is actually formed has got a different thickness and composition. And then the quantum well which is formed radially has got different thickness and composition. So that's why you end up having emission of light at 2 different colors, particularly in the infrared region of the spectrum, where these wavelengths are important for optical fiber communications, for example. Till now, you still don't see any narrowing of the line width which I was showing you in the lasers or so. So they're acting like a single nanowire light emitting diodes, but not like lasers. And the question is, why is that? It turns out that when you put metals to be able to make ohmic contacts to inject carriers, metals have got large optical losses. And these optical losses create a cavity loss here. And that means you have to pump them harder in order to be able to really make these to lathe. In the process, you're creating a lot of heat. And that means the gain goes down and you have to pump them harder. It becomes like a vicious circle. So now I got a new student, Nikita Gagrani, who came from IIT Kharagpur. And then she's now exploring how to minimize or avoid using these metals and use something like a transparent conducting oxide. Professor Hideo Hosono has spoken about, and then see how to minimize optical losses so that we can be able to make electrical injected nanowire lasers. And hopefully in a year or 2, I'll be able to really share some exciting results on electrical injected nanowire lasers if Nikita makes it successful. And before Insuk has finished his PhD, and he also tried to make, instead of using a single nanowire LED, he tried to make nanowire LED arrays. See, these nanowires are grown vertically. You fill these ones with the polymer material, and then etches selectively, put some indium tin oxide, and put some metal on the top and the bottom, injects current. And again, you can see that the IV characteristics is showing like a diode-like behavior. And again, as and when you're injecting current, you're able to really get a higher amount of light coming out of these ones. You can in fact look at the close-up of these ones. You can see below this probe, you can see bright light coming of these ones. Once if you embed these nanowire LEDs in a polymer, we can peel these things off and they can be used for flexible displays, for example, for flexible phones and flexible computers and other things. In fact, Samsung was interested in that one. So that's why he focused on these flexible LED devices or so. So now let me move towards terahertz radiation. And terahertz radiation is, 1 terahertz is about 300 microns in wavelength. And then it is, the electronics is up to microwaves and millimeter waves. In the case of optics, we've gone to UV to visible to infrared. There was a gap called terahertz gap. And then people only during the last 20 years or so, technologies have been developed, and we others and have been looking at this one. So it turns out that many of the chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum. And so that lactose and anhydrate and monohydrate and other things, particularly including explosives and otherwise also drug molecules and all sorts of things, for example. Terahertz radiation is reflected by metals. In fact, nowadays people they don't use X-rays because X-rays are ionizing radiation, because terahertz radiation is a non-ionizing radiation. So that's why people are using these in the airports and others to be able to detect the metal detectors using terahertz radiation. You can also use for biological imaging applications, for example, looking at the cavities in the teeth, and for wireless communications where you can download lots of information and without any cables onto your smart devices. Also, you can detect a water vapor in the water content in the leaves. So thereby you only water the crops whenever you need rather than just wasting the precious resources like water, for example. This is a joint work with Oxford University, Professor Michael Johnston and Professor Laura Hertz's groups here, there. And this is work of my student, Dr. Kun Pang, who is a postdoctoral fellow in Oxford now. And then we have been looking at making terahertz detectors. So here's a case where Kun Pang has taken one of the nanowires and transferred them onto a quartz substrate and then tried to make contacts using electron beam lithography. Then we shine the laser light on this nanowire and then generate photocarriers. And then terahertz pulse afterwards terahertz electric field of the terahertz pulse is the one which separates these carriers. We can measure the photocurrent as a function of time. If you can measure the current as a function of time, you can get the information about the electric field of the terahertz pulse and also conductivity of the material. In fact, we started looking at this one as a terahertz spectroscopy to measure the electrical conductivity of the nanowires without making any contacts. But then we asked ourselves, can we really detect terahertz radiation using the single nanowires? Because terahertz radiation is about 300 microns in wavelength, but we are really dealing with 300 or 200 nanometer diameter nanowires, about 3 or 4 microns long or so. So to cut the long story short, and in fact, we demonstrated that you can really make broad bandwidth, phase and amplitude sensitive indium phosphide and gallium arsenide nanowire detectors. And most recently, Kunpeng during her postdoctoral fellowship has demonstrated these polarizations resolved terahertz detectors. Instead of having one set of nanowires, and she was able to put these orthogonally 90 degrees of these nanowires. You can see the close-up of the electron microscope image here, and then to connect these ones to these bow tie antennas here, and then try to really characterize both X and Y polarization, for example. If you take a terahertz metamaterial, you shine light terahertz radiation through this one, and on the other side, terahertz transmission is taking place here. You can measure both an X and Y polarization simultaneously using our terahertz detector, which has got both ability to be able to do that. And here is a case where, in fact, some of the SEM pictures of the terahertz metamaterial Kunpeng has fabricated, and then the theoretical simulations show that the transmission and need to be X polarization and Y polarization will have these types of transmissions theoretically, and experimentally also we're able to show, and we can really be able to really mimic these ones and using our terahertz detectors, and we published this work last year or so. Really, this opens up opportunities for us to be able to make high resolution and amplitude and phase and polarization sensitive terahertz imaging systems, and that's where the industry is interested, and that's what we're exploring with our colleagues at Oxford University. Let me now move towards solar cells and nanowires. And why are we interested in nanowires for solar cells? It turns out, if you take the nanowires, and the nanowires also have got anti-reflection properties, so that means you don't really need to put any anti-reflection coatings or anything. The second thing is that because of the large refractive index of the nanowire, and then the surrounding medium is 1, so that means you're able to couple the light very efficiently. These nanowires act like light funnels or light concentrators. But also that when you're making a thin film solar cell, for example, you need to make the material thick enough to be able to really absorb all the light. And now you got a PN junction, and the carriers need to migrate long distances, and you lose some of these carriers. But whereas in the case of nanowires, you can make the nanowire as long as you want to absorb the light, and then you can create a core shell PN junction. So that means carriers can be collected within tens of nanometers or so. So really, for the first time, these allow us to be able to decouple light absorption pathways and carrier collection pathways. So that's why we're interested. And so here's the case again. Dr. Sudha Makapati was leading our laser work and also this particular this solar cell work as well. And now she's an associate professor in Monash University. And you can see these nanowires. And then we looked at what should be the height of the nanowire, what should be the diameter of the nanowire, and what should be the pitch of the nanowire. You can see that most of the current is generated at the tip of the nanowire, indicating that you don't need to make a very long nanowires. 1 or 2 micron long nanowire is more than sufficient, for example. So again, we looked at what should be the diameter of the nanowire and what should the pitch or the diameter to pitch ratio. And then you can see that diameter, about 150, 160 nanometers is ideal. And again, diameter to pitch ratio is 0.5 to 0.6 is ideal. Again, the challenge is how to make contacts to these ones. And again, you've got the nanowires here and fill these ones with the polymer material. And again, selectively etch this one, put some indium tin oxide and the metal contacts at the bottom, and you shine light and look at the solar cell efficiency. To cut the long story short, and one of our colleagues from Technical University of Eindhoven and FOM Institute in Emalf, and Professor Rick Bacchus and Professor Eric Garnett, they've demonstrated one of the most efficient nanowire solar cells with efficiencies of 17.8% or so, which is looking extremely promising in terms of making use of them for flexible solar cells and a range of applications. So that's what we are working with our colleagues at Oxford and trying to really make use of these ones for flexible solar cell applications also. So now let me finish off with my last topic.
Jagadish?
Yes. Yeah.
Can you, in another 2-3 minutes?
Okay, sure. Okay, thank you.
Yeah.
So basically, in this case, this is the work of Dr. Vinny Gautam, who used to work in my group, and then she's now at Melbourne University as a lecturer. All of us have got about 80 billion neurons. And then whenever you got a brain damage, what happens is that we are making the neuronal network. And then if you really, we asked ourselves, can we create a neural patch and be able to really make the connections back and be able to bring the functions back for people, those who got a brain damage and other problems. So this is where Vinny has really grown these neuronal neurons on nanowires of indium phosphide. These are ordered patterns here. You can see neuronal cell, and then these neurites really follow these patterns beautifully here. Instead of using a single neuronal cell, and if you use multiple neuronal cells in this box where the nanowires are, and these really form into these axons are really following these patterns beautifully. What Vinny does is that she takes this videos of this calcium imaging, and she puts a calcium dye. As and when these neurons are really firing action potentials, calcium ions are passing through the ion channels, and then you change the fluorescence intensity of this particular calcium dye, for example. She looks at if this neuron is firing, what's happening to this neuron and this neuron, and then in the process, she creates these correlation maps. When the neurons are really grown on glass substrates, the change in fluorescence as a function of time, they're all firing randomly, and there's no correlation whatsoever. But whereas these neurons are grown on indium phosphide nanowires, and then they're all firing at the same time, showing that there's excellent correlation is taking place or so, indicating there is some sort of a synchronized and correlated activity is taking place. When Winnie presented this work a couple of years back in a neuroscience conference, and they asked what neurons you're using, she mentioned that she's using rat neurons, and they said, why are you wasting your time? How about using human neurons? And in fact, now we are working with our colleagues in Melbourne and Monash and Wollongong, and working with the neurobiologists and stem cell biologists and the also computer scientists, and taking the Alzheimer's patients' stem cells and healthy people and creating mini brains, and then looking at their properties in terms of signaling behavior, and using deep neural networks to really try to understand the differences between the Alzheimer's patients and healthy people, and trying to develop the new algorithms to be able to stimulate the brains of Alzheimer's patients so that we can help them. This is really, truly exciting and multidisciplinary project, and we're having really great fun. In conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale, and developing a new class of lasers and terahertz detectors and integration of optoelectronic devices on various platforms, and developing solar cells and engineering the neural networks or so. With that, I want to thank you for your attention, and I'm happy to answer any questions you may have.
Yeah, thank you, Professor, for a wonderful talk. And as you have covered almost all the application related to nanowires, and nanowire solar cell was very interesting, and also the nano antenna where you can actually get a vertical emitting nanowire laser, that was interesting and open to audience for discussion. And there is one question posted to Dr. Jagadish. If a nanoparticle exhibits autofluorescence in ultraviolet range, it can't be used for in vivo imaging. Since for in vivo imaging, a nanoparticle had to exhibit autofluorescence in IR range. So what is your suggestion regarding how to use a nanoparticle exhibiting fluorescence in UV range for in vivo imaging?
Okay, so that's a very good question. And of course, whatever we are doing, first and foremost, you need to really use biocompatible materials whenever you're dealing with these things. And it turns out also indium phosphide nanowires, which we're using, and they're turned out to be biocompatible, but whereas gallium arsenide is not biocompatible, for example. And again, also that's where when you're looking at nanoparticles, and first and foremost, you need to check and make sure they are biocompatible or not. Otherwise, you create a lot of problems for people, for example. The second thing is that different materials or the different nanoparticles have got fluorescence in the different regions of the electromagnetic spectrum. It's a matter of choice of choosing the right material so that you'll be able to really fluorescing at a particular wavelength, which is of your interest. And so that's what I would suggest you to be able to explore and then see, first and foremost, is it biocompatible? Second thing is that which materials are fluorescing in what wavelength region? As you know, that different materials have got different fluorescence wavelengths. And also people are also doing lots of upconversion materials of doping them with ytterbium and other materials. And they're able to really be able to change also the fluorescence wavelength and other things as well.
Thank you.
V. Gautami raised her hand. Miss Gautami. Hello, Gautami. Hello. Next, Kavita. Kavita, or she also raised her hand. I think she has a question. Please go ahead, Kavita. I think they're unable to. Yeah, my question to this question is already answered now. Yeah. Looks like there are no more.
Yeah, if there are no other questions, thank you for a wonderful talk and enlightening us with the nanowire fundamentals and the applications. And I think most of the participants would have motivated, and we look forward to read more of your papers and publications. Thank you, sir, for your time.
Okay, thank you very much, Professor Shanti, and also Professor Kiran Mangalampalli, and also Professor Karthikeyan, and all my colleagues. Thank you very much, and good luck with the conference.
Thank you, sir.
Thank you.
Thank you. Bye-bye.
Yeah, I'll just, he's there. Yeah, he's there. A very good afternoon to Professor Hideo Ono, and welcome all to the next keynote address, number 4 in this conference. And I have great pleasure in inviting you all and introducing this speaker to the audience. Professor Ono was appointed president of Tohoku University in April 2018. Prior to being appointed as president, he served as vice president and as director of the Research Institute of Electrical Communication at Tohoku University. President Ono received his PhD from University of Tokyo in the year 1982. After working as lecturer and as an associate professor at Hokkaido University, he was appointed as professor of engineering at Tohoku University in 1994. In 1995, he was appointed as professor at the Research Institute of Electrical Communication in Tohoku University. He is currently the director of Center for Spintronics Integrated System, the director of Nanoelectronics and Spintronics Research Institute of Electrical Communication, Tohoku University. His research interests include physics and application of spin phenomena in semiconductors and metal-based nanostructures. In recognition for his achievements by his peers both in Japan and abroad, President Ono received a number of awards, including the IUPAP Magnetism Prize in 2003, the Japan Academy Prize in 2005, and the Leo Izaki Prize in 2016. Acknowledging him as an outstanding faculty member, Tohoku University conferred on him the honorific title of Distinguished Professor in 2008. He also has been a fellow of the Institute of Physics since 2004, and honorary professor of the Institute of the Institute of Semiconductor, Chinese Academy of Sciences since 2006, a fellow of the Japan Society of Applied Physics since 2007, and a fellow of the American Physical Society since 2012. The IEEE Magnetist Society named him a distinguished lecturer for the year 2009. Recipient of EPS Europhysics Prize jointly with David Arshallem and Thomas Dyer for their work on ferromagnetic semiconductor spintronics. Recently, in 2020 Web of Science, he received Clarivate Citation Laureate for his huge number of citations and high index. In his new role, President Ono will endeavor to make Tohoku University as an institution that is universally respected for the quality of its research and educational standards, and that continues to address the challenges of the modern world by driving creativity, innovation, exploration, and discovery. In particular, he will ensure that the university plays its part in developing innovations that will empower the local community's recovery from the Great Eastern Japan earthquake and lead to a bright future for Japan and the world. And we are proud to state here that he's a candidate for Nobel Prize for his outstanding research on photonics. And we are honored to have you here, sir, for this session, and we welcome you to deliver the talk.
Well, thank you very much indeed. Can you hear me?
Yes, yes.
Wonderful. So thank you very much for the kind introduction, and I would also like to thank the organizers for this wonderful opportunity to speak to you at ICONN, International Conference on Nanoscience and Nanotechnology. So my subject here is spintronics nanodevice from small to smart. But before going into the main subject, let me briefly introduce you our university, because I am, after all, president of Tohoku University. So it's my job to let people know about our university. So this is our university. Our university is located in the city of Sendai, 300 kilometers north of Japan, and the population is about 1 million. We are the third oldest national university in Japan, established in 1907. And we are also the first Japanese university to accept a female student back in 1913. And the operation budget of our university, except for the university hospital part, is approximately $1 billion annually. And we are a comprehensive university with 10 different undergraduate programs and departments. From the ranking point of view, you can see that we are ranked from number 1 to number 5 in Japan alone, and well regarded, hopefully very highly around the world. And the third thing that I would like to briefly mention is that we are on our campus, there's a building going on, which amounts to a synchrotron light source, the third generation synchrotron light source, which will be operational in 2023. So I'm hoping that I can see many of you here in Sendai on campus of Tohoku University in the future. Okay, so back to my talk about the spintronics nano device from small to smart. These are my collaborators. I have many collaborators around the world, and I could only show you a small part of it. And the work has been supported by the Japanese government and another various funds from the government. So I have divided my talk into 3 parts. First, I will give you, to some extent, an introductory part, 1/3 of it, what spintronics is delivering at the moment. And the second part will dedicate it to the small, making it smaller. And the third part is making it smarter. So I would like to focus my talk on information processing. And there are a number of other applications that spintronics are being used or are being researched. For example, a sensor device that can sense at the moment the magnetic field from the heart pulse. And people are aiming at sensing magnetic field from the brain itself. But these are, because of the application, the variety of application is very wide, and so I would like to focus on the information processing part. So this is, these are the things that we need to deal with, whether you like it or not. There will be a number of Internet of Things sensors all over the place, and that will create a big data, and they're all communicated through 5G or beyond. And we need AI to process all the information that we gather. So this is this scheme can be very bright if we can use it in a wise way. However, one concern is that they actually consume a huge amount of power. So you can see this slide, like that internet connected devices produce 3.5% of global emission within 10 years and 14% by 2040. A communication industry responsible for 20% of all the world's electricity in 2025. Data centers consume 1/5 of Earth's power in 2025. So basically, what these statements say is that we have to deal with this. Otherwise, we cannot enjoy the extension of this IoT, AI, big data, and 5G and beyond. For example, this is a schematic diagram of the planned data center in Sweden. Half of the data center electricity, or even more, goes into cooling the data center. So in order to save the power, people love to install those data centers at those locations that you can cool things down. So either waterfront or like as you can see, like these locations, which is reasonably cold. Another thing is that consuming a huge amount of electricity is not the only issue. And for example, if you think about autonomous driving, this TOPS, trillion operations per second performance, is important. And level 5 autonomous driving, which is basically you don't have to do anything to drive a car, that requires 1,000 TOPS. And current technology gives you only 1 TOPS per watt. So which means that in order to install more than 1,000 TOPS performance in a car that you drive, it requires 1 kilowatt of electricity. And that's prohibitingly high. And this is another reason why you have to cut the power down. And the reason why we have such a large power consumption is because we do business, or we do our work under this sort of situation. We keep all the lights on, regardless of you're using only very small part of the building. You have to keep in the current electronic system in order to process information. We have to keep all the lights on. And this is because the current working memories, which are great, DRAM, it gives you dense memory, SRAM, it gives you fast memory. This F square is feature size. So if your feature size is small, it requires only, DRAM requires 1 bit, requires only 6 feature size squared. But the drawback that all these current great working memories is this feature. They're volatile, which means that once you turn off those memories to save the power, all the information that you kept in those devices are gone. So what we would like to do is to do information processing even in a processor. Those parts that we are not using, we want to turn the light off. And that will save actually a very large amount of power. I will not go into the detail of how power is used within a processor, but standby power, just keeping information in the processor, requires a huge amount of power. So we want to do something about it. And this means that we need to have a non-volatile memory that will save the world. We actually do have a very good non-volatile memory on the leftmost panel column, which is NAND flash memory. We all have our NAND flash memory in our cell phone, or USB memory, or in our computers. But as you can see, the good NAND memory gives you a very cost-effective, not expensive bit. But it also comes with a price that 1 bit you can only rewrite 10 to the 3 times. And the power that requires, or the voltage that it requires to rewrite your NAND flash memory is always very high compared to 1 or 1.2 volt power supply. of other electronic devices. Okay, and the device that I would like to describe to you and the materials itself is this spintronics-based MTJ, magnetic tunnel junction, which will be, you can operate it at relatively low voltage, which means that the ordinary supply voltage is good enough. And endurance part, we can rewrite it 10 to 15 times or more, which is good for working with high-speed processors. So this spintronics non-volatile memory is currently the only known alternative for those DRAM and SRAM volatile working memories. So this is a schematic diagram of magnetic tunnel junctions that I just mentioned. The green and blue part are metal magnets. So now I'm switching gear to metal arena rather than semiconductor talks that we had in the previous two talks. So the green and blue are separated, these are metals, and separated by a thin insulator, which is colored pink here. The resistance of this, well, the insulator is thin enough so that we can get our electron tunnels through this insulator. And the resistance of the device here has high resistance if the magnetization is parallel to each other, and low resistance magnetization when magnetization is anti-parallel to each other. The state of this parallel and anti-parallel can be manipulated by flowing a current beyond a threshold. In one direction, it gives you parallel configuration. The other direction, you can switch it to anti-parallel configuration. And the device itself has to work with a transistor, as you can see in this slide, that this will give you only high and low resistance, and it will not work as a switch. People were looking for magnetization perpendicular to the plane. So perpendicular to this device dimension, lateral dimension. But people were having a very hard time finding a good material system to do this without sacrificing other features that we want magnetic tunnel junction to have. So back in, let's say, 90s and late and 20s, well, let's say 2000, we were working on magnetic semiconductors. So this is a completely different material system. But what we wanted to show and successfully shown was electric field control of magnets, because we can change the number of carriers, as we all know, working in semiconductors. And these carriers mediate magnetic interaction. So if we reduce the number of carriers, we reduce the magnetic interaction, which means that we can control magnetic field, electrical control of magnetic properties. So this naturally means that the target material has to be thin enough so that we can control the carrier concentration of the entire target thin film. So in this indium manganese arsenide case, we have chosen the material thickness to be about 4 to 7 nanometers. And naturally, we wanted to do the same thing with a metallic system, although in metals, the electron concentration is so high that usually applying electric field doesn't give you much of a change. But very fortunately, in our case, we have observed a significant change of magnetic anisotropy, the direction of the energy landscape that determines the direction of magnetization. And during this work, because we want to make metals so thin, in this case, cobalt iron with 10% or 20% of boron, we wanted to make it as thin as possible to see the electrical control of ferromagnetism in metals. And we actually hit something else. So this slide shows on the right-hand side, we have made cobalt iron boron thickness thick on the top panel, and the bottom panel, we made it as thin as possible. When it becomes too thin, it loses its ferromagnetism. And when it's thick, it's governed, the anisotropy of magnet is governed by shape anisotropy, which means that your magnetization lies always in plane. But somewhere in between, we have discovered that your magnetization is actually perpendicular to the plane, which people were looking for in a material system that is good enough for magnetic tunnel junction. This is because of the interface anisotropy. So there's a structure, electronic structure in at the insulator metal, in this case, cobalt iron interface, that makes your magnetization perpendicular to the plane, as you can see in this pinkish arrow, two arrows. The only thing we did was to make cobalt iron boron thin enough. But people haven't explored this region of thinness. And we hit the, well, in a sense, jackpot in a very conventional material set that people all over the world were working on. So here we have demonstrated a 40 nanometer device with, I will not go into the numbers here, but with reasonable characteristics. That is well suited for integration purposes. So we went ahead using these devices and came up with a processor that can work below 100 microwatt. So 100 microwatt is important because we want to see our microprocessor working at low power, so low that we can generate the power from ambient, like, of course, light is one source, heat difference is another, and there are many sources that we can harvest from the environment, and the maximum power is usually 100 microwatt. So we can operate our semiconductor processor utilizing magnetic tunnel junction technology. So we are combining CMOS technology with magnetic tunnel junction non-volatility, so that we can turn off our memory whenever we don't, or let's put it the other way around. We can turn on the memory whenever we need it, but otherwise we keep the power off. And that's the reason why we've been successful in demonstrating such a low power processor with actually high processing performance in terms of frequency. Okay, these are other demonstrations. I will not go into the details. The thing that we tackled next is that we've been able to show that we can produce, or at least demonstrate, on 300 millimeter wafers, integrate those magnetic tunnel junction non-volatile memory devices, so to make our integrated circuits extremely low power, like 1/100th of power. But the next thing that we had to demonstrate is to show the industry and show the world the limit of our approach, how small we can make those magnetic tunnel junction. Because industry is interested in the scaling meaning how small you can make those things. And so far, I have only shown you 40 nanometer device. They want to see how far we can go with what sort of technology and what sort of materials. Well, it's very understandable because the industry is developing this tools that cost you 10 or 20 million dollars, and in order to develop these things, it becomes a major investment, and they want to make sure that technology has a future. Also, they do not want to use new materials, hopefully, because it costs you more. So we tackle this challenge, and the thing is that here we have a two states, parallel and anti-parallel configurations of magnetization in a magnetic tunnel junction, and this is separated by an energy barrier that makes the device non-volatile. So this energy barrier has to be much greater than K over KBT. And we all know, well, in magnetism, we all know that this energy barrier is proportional to magnetic anisotropy and times volume, or the area. In our case, it's area because our source of energy barrier is coming from the interface. So you can easily expect that this will be the case. So when you make the junction diameter smaller, at some point you will lose this energy barrier. And when you scale it down to, in this particular case, near 10 nanometers, you will lose non-volatility. Remember that E over KBT will be in your exponential. Which means that your time constant is proportional to exponential of the C over KBT. So 80 or 90 versus 20 makes a very, very large difference. And for many applications, this E over KBT has to be greater than perhaps 80. And below 20, it's absolutely not usable as a non-volatile memory. So this appears to be a natural consequence of physics. And so our task is to make E over KBT, or energy barrier measured by KBT, greater than, let's say, hopefully 80 at around 10 nanometer junction diameter. Let me say a few words about this junction diameter. This junction diameter of, let's say, 30 nanometer sounds to you very big, because people are talking about 14 nanometer technology or below 10 nanometer technology in semiconductor industry, and 5 nanometer technology, and so on and so forth. They're talking about a gate length, and the device size is much greater than the gate length. So the rule of thumb here is that you need to divide the number that I'm talking about here, junction diameter, divided by approximately 3, in order to compare the number with those advertised, let's say, gate lengths. So if I say 10 nanometer, which means it's almost close to 3 nanometer gate lengths, and that's not many have demonstrated 3 nanometer gate lengths. Okay, so the question is, how do we do this? And many of you actually already know the answer. You can invent this device by yourself. So here's a chart that I have formulated. This red is high E over KVT, which I call delta here, and blue is low E over KVT. So what we would like to have is red, and that's a color code. That's a meaning of color code. And here's the thickness of our cobalt ion boron. Because, as I mentioned earlier, when we make this cobalt ion boron thickness thick, the shape anisotropy wins, and which brings your magnetization in the plane, and all the magic is gone. So you have to keep the thickness thin enough in order to make this delta high or in the red regime. And basically what the experimental results that I have shown you in the previous slide is reproduced by the simulation. But there's a huge phase space that remains to be explored. And you can, when you go through the numbers, you can see that there is another part or another region that you might want to explore in this small d range, beyond 120, for example, below 10 nanometers, that result in more than 120 E over KVT. The reason why I said you can invent this is because this is actually a bar magnet. You have, let's say, 6-7 nanometer diameter with 20-25 nanometer tall magnetic tunnel junction, which is basically a bar magnet. And we all know that bar magnet magnetizes itself in the direction of axial direction. It never magnetizes in the direction perpendicular to it. And this is because now the shape anisotropy that we are fighting against with interface anisotropy has changed the sign, and we can utilize it to get this small magnet. So we've been working on it, of course, making it small, less than 10 nanometers, and making it long, more than 15, 20 nanometers. It requires a lot of technology development. So it took us almost 3 years, but eventually we've been successful in showing that our theory is indeed true. So below 10 nanometers, or even below 5 nanometers, we can see that our device have very good non-volatility, or E over KVT. And these are the TEM micrograph, and you can immediately see that the dimension here is not as small as I have just said, because there is a dead layer at the wall, so the actual dimension of the device or diameter of the device, or electrical diameter of the device, is much smaller. And another thing that you can see from this device, TEM, is that we still have to work on those shapes around here in order to integrate them in a closed pack form. But in any case, we have all the materials there as designed, and it works very well. Like this is a diagram that shows that you can electrically switch those magnetic tunnel junction down to 8.8 nanometers. And we have recently went below 5 nanometers, which means that this rule of thumb, if you divide it by 3, we are now below 2 nanometer or gate length regime compared to those transistors. There are other issues like how tall we can make and what are the physics that comes in when we make it too tall, and how to overcome it. But because of the interest of time, I will move on to the third topic of my talk, which is making smart or new computing paradigm, exploring new computing paradigm with those devices, new devices based on spintronics. Okay, these are examples of brain-inspired computing with spintronic devices. The leftmost part is showing analog memory for memristors. Through rightmost part is utilizing stochasticity. We've been involved in 3 of those approaches out of 4. But again, because of the interest of time, I would like to concentrate on this stochasticity part. Okay. Now remember that our device becomes very unstable below, let's say, once the energy barrier is lower than kBt for a certain amount, let's say 20, which means that we have a telegraph-like noise. So stochasticity is here. So how are we going to use it? Well, Richard Feynman in 1981, in his famous talk about simulating physics with computers, he discussed about quantum computing. But he also, in the same talk, discussed about probabilistic computing. So basically, what you want to do and what you need to do is to design things in such a way that you can get this energy landscape. The lowest part of energy portion of energy landscape gives you the answer to the question or the solution to the question. So the lowest energy state is most frequently observed, and so you observe the system and you get the answer or solution. So procedure of this probabilistic computing is such that you need to define an energy landscape, or people call it cost function as well, for each given problem. So you have to design things specifically for your problem. And this mapping the cost function to a physical system with probabilistic nature. In our case, very often it's called stochastic neurons. And in our case, our magnetic tunnel junction plus a transistor associated with it. So, and then acquiring statistics, and the most frequent state that is showing up is your solution. So the equation is such that we implement this energy landscape into interacting stochastic devices and observe the probability in those states, and we get, in this case, 2 answers of equal probability. So what we did was we made the device. We made into a p-bit, we call it, probabilistic bit. Then we connected those p-bits by synaptic weight logic, and we implemented the cost function to the system. The example we have shown recently is integer factorization. So it's an illustrative example of optimization problem. Well, in retrospect, integer factorization might not be a very good example because people expect integer factorization to be exact, and it is indeed exact. But here, we can only give you an approximate answer where you need to look for the answer. When
Professor, sorry to disturb. Can you take another 3 minutes to wrap up?
Okay, all right.
Thank you.
Thank you. So in order to well, you can only get an approximate answer. So but in any case, we have shown that you can do this by stochastic magnetic tunnel junction. As you can see, we made various kinds of magnetic tunnel junction to control its stochasticity, and we have applied current and made sure that it can be the stochasticity can be controlled by the current. So we made it into devices, shown on this slide, which we call it p-bit. And this p-bit, depending on what sort of input voltage or input current you have, it gives you mostly antiparallel state or mostly parallel state, and somewhere in between, depending on the current flow that you have in the system. So that's your p-bit. We connect this p-bit through the synaptic weight logic. Basically, it's a microcontroller, and we all connected all p-bits that we have. Actually, we made circuits up to having 8 p-bits. 8 is a small number, but I'll show you that you can actually factorize a reasonably good big number. So these are our device, stochastic device. We connected with the synaptic weight logic, with microcontroller, and implemented an algorithm into it, as shown here. So this time, I want to. This f is the numbers you want to factorize, and x and y are the numbers of the solutions. So in order to, I will not go into the details because I only had 3 minutes a couple of minutes ago, but these are the factorizing 35 and weight functions, and the important part is that this you can implement it into a quantum annealer, but it's extremely difficult for if you do it on quantum annealer because it's this 3-body interaction is not physically easy to implement in quantum annealer. So we have an advantage here. So these are the results. As you can see, we can factorize 35, 161, and 945. That's the maximum number, 945, we can factorize by 8 cube p-bits. So, so these are the comparison with a quantum annealing machine. We can do it at room temperature. We can implement many body interactions much more easily than they can. We have a manufacturable base that megabit to gigabit level, because the only thing that we used here is the STT-MRAM or MRAM, or magnetic random access memory, utilizing magnetic tunnel junction, and the industry is already working on 1 gigabit level. So all we need to do is to connect it appropriately and make it much more unstable than they are now. We do not have quantum supremacy because these devices are classical. So people always argue, but that it doesn't have the future. But remember that we have a gigabit level integration technology already in our hand, and we do not know at the moment what sort of solutions, optimization we can do with those gigabit level technology. If this gigabit technology provides you a system solution that is capable of solving a system that is big enough to many applications, we can use it until the quantum people catch up. Okay, so what I've been discussing about is spintronics technology working with the CMOS technology in the era of 5G, AI, big data, and IoT. The system at the moment requires a large amount of power because the core is hot, your memory is consuming a huge amount of power, even if they are not doing anything. But I tried to explain to you and convince you, hopefully, that with spintronics technology working with CMOS, we can make things much, much greener, orders of magnitude greener. And also, we can make those computing schemes that are not readily available to you through CMOS technology. So, well, thank you very much for your attention.
Thank you, Professor, for the interesting lecture. And we are really privileged to listen to your talk, sitting over across many miles away. And we are really thankful for you today for being here and enlightening us with a very simple, fundamental, explained very neatly. So you just took us right from CMOS and spintronics and the challenges in making it small, and by making it stochastically magnetic channel junction by controlling with current, how we can make it smart. And we really enjoyed your session, sir. There's a few questions for you. One question. Although nowadays we have better controllability in qubits at room temperature up to few seconds, nevertheless, significant lower spin polarization loss time is a big challenge in most of the spintronic devices. Can you let me know the relaxation time limit achieved in your system, specifically at room temperature?
Okay, well, thank you very much for the question. Well, here, I am trying to make our magnetic tunnel junction as unstable as possible. Of course, there's a limit. The limit is there because we have to do some calculation in order to transfer this information to other qubits. But that's usually fast enough with CMOS. So we want to make this instability as small, well, as fast as possible. Here we used milliseconds, but we would like to have it below, let's say, microsecond. And that's very different notion of quantum coherence that you have in qubit in the quantum system. In quantum computers and quantum systems, it's extremely difficult to let many qubits interact each other. So that's the challenge. And here, even the largest integration so far reported can go up to, let's say, 100 qubits, if I remember correctly. But remember that the technology that I have just showed you can easily go up to 10 to the 9 qubits. So the system and also the interaction that we can implement among those qubits is done by electronically, and it has much more freedom. So I would tend to believe that in the end, qubit might be better approach, but we do not know how many years we have to wait until our technology get to that level. Meanwhile, the technology is already in our technology is already here. So thank you very much for your question.
Thank you. Anybody else? sharing.
Yeah, you can continue.
And on behalf of the participants, thank you for the amazing lecture, and you've got in chat also people are congratulating you for your amazing lecture, and they're very happy to listen to you. Thank you, sir, for your time. Thank you.
Well, thank you very much, and
So,
have a great time with the conference. Thank you very much.
Thank you, sir.
On behalf of the organizing committee, I wish to thank Professor Shanti Prince from the Department of Electronics and Communication Engineering, SRM Institute of Science and Technology, for chairing the keynote session. Thank you very much, ma'am. Now we have greeting messages from our co-organizing institutions. I request Professor Karthikeyan, Professor from the Department of Physics and Nanotechnology, to take over the session. Thank you.
Good afternoon, one and all. Can I share the screen? Good afternoon, one and all. It is time for the greetings from one of our conference associates, Professor Yasuto Shirai, Shizuoka University, Japan. I request him to his message now.
Okay, good afternoon, everyone. Well, can I show my screen?
Yes.
Okay, thank you. Okay, so welcome to ICONN 2021. I would like to welcome you all as a representative from Shizuoka University, which is in partnership with SRM Institute of Science and Technology holding this wonderful event. Can you see the screen? Can you see my slides?
Yeah.
Oh,
Yes,
okay, great. Okay, I am talking on behalf of Shizuoka University, which is one of 86 national universities in Japan. Well, the Professor Ono, who just spoke right now, he comes from Tohoku University, which is a very prestigious university. Our university is the same as Tohoku University in the sense that we are both national universities, but Shizuoka University is, well, more localized university based in Shizuoka. Well, in this picture, you can see Mount Fuji, which is the highest mountain in Japan. And our campus is located in Shizuoka Prefecture, in which half of Mount Fuji lies. Okay. I'd like to take this opportunity to introduce our university a little bit. Okay, so we have 6 faculties, and we have another School of Regional Development. And we have in total about 10,000 students and also a little over 1,000 staff members. And among the 10,000 students, about 460 come from abroad, and out of which most of them come from in Asia. Well, Asia, by Asia, I mean Eastern Asia, like China, Korea, and Southeast Asia, and also South Asia, including India. And actually, we have received quite a few from India, especially from SRM Institute. And we have been developing a very close tie with institutes in South and Southeast Asia as well. Okay, this is to indicate some our close collaboration between SRM and Shizuoka University. We signed an MOU in 2013, but well, our relationship on the personal level started some years before, even before this. And ever since we signed our MOU, we have enjoyed very active exchange activities between the two universities. We have activities on the faculty level as well as student level. And we have so far received over 100 delegates from SRM. And also we have a very strong academic program, a double degree program between the two universities. And Shizuoka University have so far received 15 students from SRM on this program, leading to PhD. And these are the pictures from our past relationship. I guess most of them were taken in the year 2016 when we co-hosted an event called Inter-Academia Asia. This Inter-Academia Asia event have been held in Shizuoka for some years, but with one exception, in 2016 when SRM hosted this event. And that event in 2016 was a tremendous success. And we had participants from over, I think, 9 countries and close to 100 or over 100 participants. And I'd like to conclude my greetings with our appreciation to SRM. Well, as I just mentioned, we have received tremendous support in Inter-Academia Asia, and they have sent us many excellent young researchers, including PhD students. And I hope that Shizuoka University can maintain this very, very close relationship with the SRM in the future. And I hope you will, this event, ICONN 2021, will be a very successful event. Well, I'm sure we have gone through very tremendous keynote speeches so far, and I just listened to Professor Ono's speech, and well, I am sure that this will be a very, very successful event. Okay, thank you very much.
Thank you, Professor Yasutoshi Shirai, for your valuable appreciation and giving your valuable time and elaborating our understanding with SRM. Once again, I thank you very much for greeting the conference. Thank you, sir.
Thank you.
Now I request Professor Dr. John Kennedy, GNS Science, New Zealand, to deliver his message.
Greetings from New Zealand. It's actually good evening for us. It's 9:15 p.m. So hope you're all having fun. Dear distinct guests and speakers and participants, GNS Science is a national lab. We call Institute of Geological Nuclear Science. It's as a Crown Research Institute. We congratulate Department of Physics and Nanotechnology, SRM Institute of Science and Technology, for organizing this 6th ICON event in association with many international and domestic partners. We have been associated with this conference for most of all the events last 12 years. And we believe this conference in its new virtual form will continue to create a unique learning opportunity and to promote effective collaboration between the postgraduate students and academicians and researchers. As we all know, nanotechnology is truly an interdisciplinary science that offers great scientific and technological potential. However, we are still having a lot of challenges to realize some of the applications in many impact areas. Following the footsteps of New Zealand-born Nobel Prize winner Alan McDermott, who got the Nobel Prize in conducting polymer in 2000, we in New Zealand, we focus our material science research into more nano-science-based research. In fact, our government is now signed up to be carbon neutral by 2050, which is not far away. So our research is now more focused on developing technologies to mitigate climate change, and looking more on sustainable energy production and storage. So we understand that this conference covers broad research themes, focusing on some of these areas as well. I'm glad to see that organizers have invited top quality speakers for this conference, even though it's a virtual event. In association with SRM, we got quite a lot of exchange from BTech and MTech students and the PhD students. In fact, we managed to employ one of their former PhD students into our scientists as well. So we hope we'll continue to engage with SRM, and we thank the organizers and extend our warm greetings to the participants. Wish you all success for this event. Thank you.
Thank you, Professor Dr. John Ken, for your appreciation and warm greetings to the organizers as well as participants. We are very happy to be with you and we value your partnership. I, on behalf of ICON Conference Committee from SRM Institute of Science and Technology, thank Professor Yashutosh Shiragi and Professor John Kennedy for their excellent support for this event and everlasting partnership. Thank you, sir. Thank you once again. Dear participants, now it is time for the parallel session, and I request all the participants and members to join the parallel session. Scientific session is about to start. Thank you. Thank you, one and all. So the keynote session concludes here in Daman today. We will meet that we will have a keynote session after the parallel session. Thank you all.
Thank you, Professor Karthikeyan. Can you please repeat the Zoom links or the links available for the parallel sessions?
Yeah, participants, we sent you a Zoom link PDF in your email ID. If you are participating, for example, in the session A, you will have a separate Zoom link for the session A. If you want to participate in session B, then you will have a different link. So you check your PDF file, which has got Zoom link, and also the schedule. You see whether you are in the section 1A or 1B, 1C, we have up to 1G. So all these sessions have different Zoom links. So you have to, if you have any presentation in the Zoom session 1A, you have to select link from the 1A. If you have presentation in Zoom link 1C, you have to select the link from the 1C. So all these 7 links are different. So please look at your email and also the PDF file containing Zoom links carefully and join your session accordingly. For participating in the keynote sessions, you have a separate link. So please use that link for joining the keynote sessions. If you have any doubt, I think you can, even during the conference, you can contact me. Thank you, participants. I hope I clarified your doubts. Please use the different links for different sessions. Thank you once again. Thank you, sir. I think the participants who are in this room can leave and they can go to their respective sessions.
Professor Karthikeyan, there is a chat, there is a query for poster presentation. Can you please clarify that?
Yeah, poster presentation actually will start by for example, for the poster presentation from poster CP1 to CP100, it will start. if the time for the poster presentation is from 1:30 to 3 p.m. in that time. Please note that the poster session starts from 1:30 to 3 p.m. Indian Standard Time. So using the Slack link sent to you, I hope you might have uploaded your posters. So the experts will visit you during this time to inquire about your posters. Please put your posters in the allotted track between 1:30 to 3 p.m. So for poster number from CP1 to CP600. Then for the poster numbers from CP601 to CP1200, it will start 5:30 p.m. So you can, I hope you have uploaded your posters. So the second batch of posters from CP601 to CP1200 will start by 5:30 p.m. Please kindly note this thing. We have sent you these details to you also as a schedule. Kindly check it and present your readings accordingly. I hope I have explained you. Otherwise, also you can chat me again. You can ask your doubts. So as I said, once again, now this keynote session is ended. So the next keynote session will be after parallel, that is, it will start by 3:10. We have completed 4 keynote lectures now. Here, keynote lecture 5, 6, 7, that will start by 3:10 p.m. So you can leave the link now and participate in your session, that parallel session. If you have any presentation, please go and participate. As I said, each session has